At long last, let's talk about normal random variables. So a random variable has the normal distribution, or behaves according to a normal distribution, with mean mu and standard deviation sigma if this is its density function. What we mean by density function is this curve here. It sort of tells us the behavior of the variable. See, it sort of says that most of the time the random variable is going to be somewhere between these marks, and then sometimes it's over here, sometimes it's over there, and very rarely is it out to the right of, say, this mark right here, or out to the left of this mark. Okay, it's sort of like a caricature of a histogram. What the heck is this? Well, if you've taken enough mathematics, then you've seen functions before. Some of you may or not have seen functions. That's okay. This is just the function of x, which is described by all of this stuff here. Okay, here you have two of the most famous irrational numbers, e and pi. And if you choose some values for mu and sigma, then you can put this into your calculator and graph it. So if I go to my calculator, let's say if I let the mean be 10 and the standard deviation be 1. If I go to y equals there, then I do 1 over quantity, the standard deviation's 1, then times the square root of 2 pi, close all that stuff up there, multiply by e raised to the negative quantity x, this is the x button, minus the mean. I said, let's say the mean is 10, close quantity, squared, and divide by 2 times sigma squared. I should really probably put that in parentheses just to be safe. 2 times 1 squared. 1 squared is 1, but I don't really need that there, but we'll do that. Now if I hit graph, I'll press the window key and I'll change my window. I'll go from, say, I don't know, 5 up to 15, and my y values will go from, say, 0 up to, I don't know, say 1. And then press the graph key there, and there you go. There's a bell-shaped curve. This value is 10. I know that if I press the trace key, then yeah, it gives me the coordinates there at 10. It just so happens that this little guy up here is marking the top of that curve. It occurs where x equals 10 and y equals 0.3989. Okay, right there. But you don't have to know this formula for this class. If you go on to take more statistics or do anything theoretical at all, you will certainly have to know this. But what we really need to know is that this is the curve that corresponds to that formula, and it describes how a normal random variable behaves. Its mean is mu, so it's centered right there, and then one standard deviation out to the right is right there, and one standard deviation to the left is right there. 2 standard deviations to the left is right there at mu minus 2 sigmas. 3 standard deviations to the right of the mean is right here at mu plus 3 standard deviations, right? And I know exactly where to make a mark 1 standard deviation out to the left or right, because, hey, this is sort of concave downward, right? It's sort of concave downward right there, and then it looks like it's concave upward out here. It's like if you had one bowl and you turned it upside down right there, and then you had another half bowl there and another half bowl there, so that this one upside down bowl is sitting on the edges of these other two. It's where they meet right here, and there is where you drop straight down and you're exactly 1 standard deviation out to the left or right. As we mentioned before, you will oftentimes encounter sort of mound-shaped or bell-shaped data, or mound or bell-shaped populations. But normal random variables are sort of the canonical, like, perfect model for those kinds of things for a lot of reasons that we won't get into, some of which we'll touch on. This is sort of the shape. These random variables arise naturally in the study of natural and industrial systems. They also arise naturally when we talk about theoretical things. A lot of statistical tests are based on normal distributions, it turns out. Okay, so they're important for doing statistics. If x has a normal distribution with mean mu and standard deviation sigma, now there are 3 parts to this. If it has a normal distribution with mean mu and standard deviation sigma, then it means that it's sort of nice, smooth, perfect histogram shape there is like this, and it's centered here at mu. It turns out the mean, the median, and the mode are all at the same spot. The mean is mu, and the standard deviation is sigma. Now I know where to come out 1 standard deviation from the mean. Once I draw my normal curve, 1 standard deviation out from the mean is always directly below this point right here, which is, if you sort of think about it, it sort of looks like this curve has sort of a concave down bowl shape there, and then it sort of turns concave up over here and concave up over here. It's where that concavity changes direction on both sides. Directly below there is one standard deviation out from the mean. One standard deviation out from the mean. So you draw the curve, and then mu is right there in the middle, okay, right under the hump, and then go one standard deviation out either side. That's mu plus or minus sigma, and then this point is 2 sigmas to the left of mu, so it's going to be mu minus 2 sigmas. This point right here is mu plus 2 sigmas, right? Because you start at mu and you go 1, 2 sigmas, okay? And then if I go 1, 2, 3 standard deviations out, I'm here at mu minus 3 sigma. And if I go 3 standard deviations up, let's see, I go mu 1, 2, 3 standard deviations up from the mean is right there. For normal random variables, if I want to calculate the probability that the random variable is between, say, 2 marks, A and B, then that probability is just going to be the area of the region here between A and B, beneath the curve and above this line. It's just this area. Hey, see, you can really think of these normal curves as boundaries, like when you're doing Venn diagrams, right? Remember, probability axiom number 2 says that you must get something in the sample space with probability 1. It's sort of the same thing. This picture here, it looks a lot like a Venn diagram, just with a curvy boundary there. See, the boundary doesn't have to be a rectangle. We like rectangles because they're easy to draw and stuff. But if I want to get the probability that I get something in here, we take it to be sort of the area of this region divided by the area of the whole. Right? Same thing here. We take the probability that we get something between A and B to be the area here between A and B divided by the area of the whole. Well, the total area beneath one of these are called density curves. The total area beneath the density curve is always 1. Okay? The total area beneath the density curve is always 100%. Okay? So suffice it to say, probability that this normal random variable takes on a value between A and B is simply the area in here between A and B. Okay? Now, it turns out finding areas beneath curves is what integration is all about in calculus. We aren't going to do that, and in fact, even if we knew some calculus, we wouldn't be able to apply it in this case because it's too hard to do it by hand. We actually need computers to do it, like your calculator, and so your calculator will do it for you like this. If you want to know the chance that, if x is a normal random variable, if x is a normal random variable with mean mu and standard deviation sigma, then the probability that x takes on a value between A and B, you can do with your calculator with the normal CDF function. You put in A first, B second, that is the left endpoint, and then the right endpoint, and then the mean, and then the standard deviation. Always in that order. Okay, it's got to be in that order or it'll be messed up. Finally, one more thing about normal random variables before we get to examples, and this is really, really important. Normal random variables are continuous random variables. Normal random variables are continuous random variables, which explains our use of the density function here. Binomial random variables are not continuous. They're discrete valued. They take on values from the non-negative integers. 0, 1, 2, 3, 4 successes, 5 successes, 6 successes, etc. Normal random variables model continuous random quantities. Things like the amount of time to accomplish a task, or maybe the amount of a fluid in a vessel, such as coffee. So let's do some examples. The amount of coffee, X, that your statistics professor drinks each day, not the number of cups, but the fluid amount of coffee that he has, let's say, has a normal distribution with mean 55 ounces and standard deviation 6 ounces. Shade the appropriate regions beneath the density function and find the following. Okay, so mean 55, standard deviation 6, mean 55 and standard deviation 6. So the first thing I'm going to do is draw a normal curve. Mean is 55, standard deviation, come down, it's probably right about there, okay, is 1 standard deviation up. Standard deviation is 6, so I come up 1 standard deviation from 55, I'm at 61. Drop down a standard deviation, I'll be at 49. Drop down one more standard deviation, I'm at 43, right? Because the standard deviation is 6 ounces, right? These are all in units of ounces. Between these tick marks, 6 ounces. 67, that's 2 standard deviations up, go up here to 73, and then come down here to 37, and we don't really need all this, I think. Let me just erase it there, and we should probably indicate our units here are in ounces. So it says, what's the chance that the amount that your professor drinks, which we're abbreviating with a big X there, what's the amount that your professor drinks is between 49 and 55? 49 and 55. 49 and 55. Okay. Well, it's just going to be the area right in there between 49 and 55. Okay. So the probability that the amount that your professor drinks is between 49 and 55. I can do with my calculator. I don't want to do it any other way. Normal CDF, I put in 49, comma, 55, comma, running out of room here. The mean there is 55, and the standard deviation is 6. Okay, so then I pull out my calculator, and this normal CDF function is in the distribution menu, just like the binom CDF stuff was. So go to second, vars, normal CDF. Let's see, 49 is my lower endpoint. My upper endpoint is 55. And my mean is 55 and the standard deviation is 6. Now if you have one of these older calculators and it doesn't prompt you for these things, then you'll just have to enter them in order like this. Okay, you'll get something like this, normal CDF, and you have to enter your left endpoint and then comma. The comma is right here above the 7 key. Okay, right here above the 7 key. And then so your lower endpoint, comma, your upper endpoint, comma, your mean, and comma, and your standard deviation. Okay, and voila, 34.13% approximately. 34.13%. Hey, you know what? By the empirical rule, I know that, this is, mound-shaped shape here, right? So this red region is, what's that? You remember? What is it? Can you quiz yourself real quick? What is it? The red region here should be about 68.27%. Okay, the black region there is half of that. So if I cut that in half, I get 34.135%, right? And I've done some rounding along the way. That's this. You see, the empirical rule actually comes from the study of these normal distributions. That's where the empirical rule comes from. Yeah, awesome. Hey, let's do another one. What's the probability that x takes a value between 55 and 61? Okay, so between 55 and 61. Whoops. Hey, you know what? I bet you I'm going to get the same answer there. What do you think? Because of symmetry, right? Probability that x takes on a value between 55 and 61. Okay, I'll put it into my calculator though just to check, but I bet you it's exactly the same because it's exactly the same size as that other piece there by symmetry, right? But if I put in normal CDF, 55 is my left endpoint, and then the right one, and then the mean, which is 55, and standard deviation of 6. Sure enough, let me just do second entry, okay, and I'll change, I've got the same mean, 55 and 6. I just need to change my left and right endpoints to 55, comma, 61, and guess what? You get exactly the same thing as we got before, 0.3413 approximately. All right, let's do another one. What's the probability that x is less or equal to 55? What's the probability that your professor drinks less or equal to 55 ounces? Again, let me get my curve there. I like to sketch this stuff as I go along. I like to draw a lot of pictures because pictures help me think. Okay, try not to erase too much of my shape there. All right, the probability that x is less or equal to 55. Gosh, just by inspection, it should be right at a half, right? Because it turns out, because it's a symmetrical distribution, the mean is right in the same spot as the median, right? The median is a point that carves the data set or the distribution into a lower half and an upper half. It coincides with the center of gravity for this case. Okay, so it should just be a half by inspection, a half or 50% or 0.5, right? Now we can also calculate with our calculator just for practice there, and we should, because you'll see that this one is we have to be a little careful here. All right, let's put in our lower and upper point there. well, gosh, what's the lower point? I'm not really sure. Our upper point there is certainly 55. It's right there. But what's the lowest value there? Gosh, you know what? One thing about these curves is they never actually touch the horizontal axis. They just get closer and closer and closer. They converge, but they never actually touch. So there really is no lowest value. I'll put negative infinity in there. Now let's get the mean and the standard deviation in there. It's still 55 and 6. And now let's see what we do here. When I get my calculator, unfortunately, there is no infinity or negative infinity key on the calculator. So I just got to get something that's really, 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 really far out. Okay, I'll put my upper point there, 55. I could choose like something like negative 10 to the 99th power. Okay, so negative. I use the little itty bitty minus sign there for the negative, right? Negative. Let me insert, all right, second, delete for insert 0 raised to the 99th, okay? And that's something that's going to be really far on down the line to the left, okay? And that'll work out just fine. There's some kind of little computational wrinkle there, and we get a 5 out here on the end, but essentially it's 0.5, okay? It should, in fact, be exactly 1/2, 0.5. Again, don't worry about this over here. It's exactly 1/2. That's what the answer is. Now let's take a look. You know that you can do this another way, arguably maybe even a better, well, different way. I'll put it that way, a different way. Instead of putting in like negative 10 to the 99th power there, like that, what I could do is say, you know what I really want is just to go far off to the left of the mean. So, you know, the standard deviation is 6, and 10 standard deviations is pretty far. So I could just say 10 times 6. Why 10? Well, because it's a lot of standard deviations, and it's real easy to multiply by 10. Or, you know, maybe I could say 100 standard deviations, which is 100 times 6. But I have to come that far to the left of the mean, right? So what I really need to do is say 55, which is the mean, minus 100 standard deviations. Or 1,000. By 100, I guess I mean 1,000. Whatever. Some large number of standard deviations to the left. Okay. In fact, I'll do it this way. I'll go 1,000 standard deviations, and you see I get the same answer as I did before. What if I only went 10 standard deviations? Is 10 standard deviations enough to get out to get most of that area? Well, let's see. Let's compare it. Take a couple of these zeros off, and now I'm just going to go 10 standard deviations out, and I get the exact same thing. So to about the 10th decimal place at least, it doesn't matter if you go 10 standard deviations or 1,000. It's going to be, your answers will be approximately the same. Again, I have to worry about this kind of thing if I see just simply this, you know, the chance that x is less or equal to a certain value. Up here, it's pretty easy, right? Because I just want to know the chance that x is between two fixed values. Okay, down here I don't have that. I just want to know what's the chance that it's less than something, or similarly if I had the concern with the chance that it's greater than something. Okay, let's do another one. What's the chance that x is greater than 65? Probability that x is strictly greater than 65. Now, if this were a binomial situation, we'd have to use the rule for complements to turn this sign around, right? But we don't have to worry about that now, because what I can do is this normal CDF function takes different input, right? I can put in my lowest value, which is 65. Now I got to go all the way to the right, which would be positive infinity. But again, remember, there's no positive infinity key. Instead, I'll just go say 10 standard deviations to the right of the mean. 10 sixes to the right of the mean. And then the mean there is 55, and then the standard deviation is still 6. And when I put that into my calculator, I get, you know, I'll do normal CDF, go in here and I'll change all this stuff around. I'm going from 65 up to 55 plus 10 sixes, right? And then the mean is still 55, and the standard deviation is 6. And hit enter. There we go. It's 0.04779. 0.04779. Okay, I didn't draw a picture for that, but if I did, it would look a lot like this, right? I'd find 65. Let's see, 65 is about here, I guess. Whoops, 65 is about here, I guess. Okay, and I wanted to know the chance that x takes on a value to the right of that mark. So that's just the area bounded by the curve in the horizontal line there to the right of 65. This is 65, okay? And so yeah, it's about 4 or 5%. That's that's what we got there, 4.779%. Now, what's the chance that x is less than 45 or greater than 65? Hey, I could replace that or with a union symbol, right? If I wanted to. The chance that x is less than 45 or greater than 65. Let me draw a picture of that. Chances that x is less than 45, which would be about here is 45, or greater than 65. 65, which is about here, so greater than 65, less than 45, okay, it's right down there. Hey, guess what? 65 is 10 up from 55, and 45 is 10 down from 55. Okay, so by symmetry, these two shaded regions here in red are the same amount. I want to know the chance that x is less than 45 or x exceeds 65. Either one. Because why am I interested in the union of these events? Why am I interested in the chance that either one of these occurs? Because, hey, you know what? I know that either way, class is going to be awful, because if my professor doesn't have enough coffee, he's going to be really boring and slow. If he has too much coffee, he's going to be bouncing off the walls and nobody's going to understand him. Now look at the picture. The picture tells you exactly how to do this. I know that the two areas are the same by symmetry. Can't we just say it's 2 times the chance that x is greater than 65? Sure. And I already know that answer. So it's 2 times 0.04779. Pull out my calculator, take 2 times the answer. Answer is second minus sign. See ANS for answer. It's 2 times that stuff. It's about 9.5, 9.6% or so. 0.09558. Ooh, popcorn's done. What about the probability that, gosh, what does this mean? What's the probability that x minus 55 in absolute value is less or equal to 12? Let's get a picture. That's what I always like to do, try to figure this out. But the probability x minus 55 in absolute value is less or equal to 12. Well, what does absolute value do? This finds the absolute distance between these two things. Okay, so where can x deviate no more than 12 from 55? Let's see, 12 up from 55 is right here, right? 67. 12 down from 55 is right here at 43. I want to know the chance that the distance between this random thing and 55 is no more than 12. That's the same thing as saying, the chance that x is between 43 and 67. I know what you're thinking. You're saying, well, why didn't they just ask that? Well, because there are multiple ways to express things, just like there are multiple ways for children to express their needs. We should try to be able to understand them all as best we can. So we're really being asked for the area right there. Okay, now your calculator won't really understand this kind of stuff. You still, again, you're going to have to enter it into your calculator, like this. Normal CDF. I already know the answer. Isn't it like 95.45%? Because of the empirical rule, right? 43 up to 67, and then the mean is 55. And the standard deviation is 6 all day long, at least in this example. So I go to my calculator, and sure enough, if I do normal CDF of 43, 67, 55, 6, and then close her up there, get that to a 55 like it's supposed to be. There we go. Press enter. Sure, 95.45% approximately, 0.9544998. Okay, so it's approximately 95.45%. Again, that empirical rule, it comes from looking at normal random variables.